periodic functions, convolution theorem, convolution product. If time permits, we can go for classroom workbook also. And even we discuss initial value and final value theorems, right? Now, let us start with the definition of periodic function. Suppose we have a function f in the variable t. We say that this is periodic function with a period capital T if t is the smallest number, or simply we can call it as t is the smallest real number, such that f of small t plus capital T equal to f of t for all t. So whenever this happens, we say that small f of t is a periodic function with a period capital T. What does it mean is, for every t units, capital T units, t is a real number, smallest real number. For every t units of time, again the function retains same values, gets same values. In that case, we call it as this is a periodic function with a period capital T. Let us see an example. Suppose if I take f of t equal to sin t. Now, suppose I can take this is sine of t plus 2 pi. This is nothing but sin t. Even I can take sine of t plus 4 pi. Basically, this 4 pi is a multiple of this. Again, this becomes sin t. Similarly, we can take again another multiple of 2 pi, that is 6 pi. So, sine of t plus 6 pi is again sin t, like this. So, basically, it is a 2 pi. 4 pi, 6 pi. This is a multiple of 2 pi. This is a multiple of 2 pi. So therefore, whenever this is true for t, it is valid even for multiples of t also. In this case, this capital T is nothing but 2 pi. In fact, this is the smallest real number, such that sine of t plus 2 pi equal to sin t for all t. Therefore, sine is a periodic function with a period capital 2 pi. Right? So whenever we have a periodic function, we can discuss its a period value. This is very, very important. So we have a function f of t. We say that this is a periodic function with a period capital T if t is the smallest real number, such that f of small t plus capital T equal to f of t for all t. So in this case, sin t is a periodic function with a period 2 pi. Note this. A function f of t is said to be a periodic function with a period capital T. A function f of t is said to be a periodic function with a period capital T. A function f of t is said to be a periodic function with a period capital T if t is the smallest real number, such that f of small t plus capital T equal to f of t for all t. If t is the smallest real number, such that f of small t plus capital T equal to f of small t for all t. Example, f of t equal to sin t is a periodic function with a period 2 pi. F of t equal to sin t is a periodic function with a period 2 pi. Now let us discuss the Laplace transform of periodic functions. So the next concept is Laplace transform of periodic functions. Suppose we have a function f of t whose period is capital T. Now in that case, its Laplace transform looks in a different way. Suppose assume that it's not a periodic function, for example, then in that case its Laplace becomes like this. Laplace of small f of t is integral 0 to infinity e power minus st into f of t dt. That means we are integrating this function from 0 to infinity. But I am saying that this is a periodic function with a period t. That means for every t units, the function retains same values. Therefore, you need not, that means below capital T, the function will not have repeated values. So after T, for every T units of time, the function regets again same values, returns same values. So, but up to T, there is no repetition of values. Therefore, my intention is you need not integrate this function up to infinity. So in this case, the Laplace of this function f of t becomes integral 0 to capital T e power minus st into f of t dt whole divided by 1 minus of e power minus st. So this is the Laplace transform of this expression is the Laplace transform of a periodic function with a period capital T. Generally, if it is not a periodic function, this is given by this definition, integral 0 to infinity e power minus st into f of t dt. But I am saying that this is a periodic function with a period capital T. That means below t, the function will not have repeated values. But after t, for every t units, the function gets again same values. Therefore, you need not integrate this function up to infinity. You can integrate this function up to t only. Whole divided by 1 minus e power minus s into capital T. So, this is the Laplace transform of a periodic function with a period capital T. Note this. If f of t is a periodic function with a period t, if f of t is a periodic function with a period capital T, if f of t is a periodic function with a period capital T, then L of f of t equal to this. If f of t is a periodic function with a period capital T, then L of f of t equal to integral 0 to t e power minus st into f of t dt whole divided by 1 minus e power minus st. Next we discuss convolution product. Suppose we have two functions f of t comma g of t in the variable t. Here t is a time variable. Now let us see the convolution product of these two functions, that is denoted by f of t star g of t. So this is not a normal multiplication. This is nothing but convolution product of f of t and g of t. This is given by the integral 0 to t f of capital T into g of small t minus capital T dt. So therefore this is convolution product is an integral. So integrate this function from 0 to small t, but here you integrate this function with respect to capital T. So capital T is another variable. So therefore f of capital T dot g of small t minus capital T into dt. So integrate this entire function with respect to capital T. When you are integrating this function, small t is a variable. Small t is variable, but capital T, small t is constant, but capital T is a variable. So integrate this function between the limits 0 to small t with respect to capital T. And this is nothing but convolution product of these two. Let us see an example. Suppose we have f of t equal to e power 2t and g of t equal to e power t. Now f of t star g of t, this is nothing but integral 0 to t f of capital T. This is f of t small t, but I want f of capital T. So this is e power 2t. I want g of small t minus capital T. So this t is replaced by t minus capital T. So therefore this is e power small t into small t minus capital T into dt. Now inside this integral, this is a constant expression. So you can take outside e power t into, this is integral 0 to t e power 2t into e power minus t, this is e power t. So therefore this is e power t into integral e power t is e power t, limits are from 0 to t. So therefore this is e power t into e power t minus e power 0, this is 1. Therefore, this expression is e power 2t minus e power t. So therefore, the convolution product of these two functions is e power 2t minus e power t. Now, let us find Laplace of f of this convolution product. Laplace transform of f of t star g of t. This is Laplace of e power 2t minus e power t, because this value is e power 2t minus e power t. So what is my intention is, I would like to express Laplace of convolution product in terms of product of Laplace of individual functions, right? So therefore, here we have Laplace of e power 2t minus e power t. Now here we have a minus symbol, apply linear property for Laplace. So L of e power 2t minus L of t. L of e power at, 1 by s minus a value 2, divided by 1 by s minus 1. Now let us simplify this. S minus 1 minus s plus 2 divided by s minus 1 into s minus 2. So therefore this is 1 divided by s minus 2 into 1 s minus 1. So this we can write it as 1 by s minus 2 into, this is normal multiplication, but this is a convolution product. This is a normal product, but whereas this is convolution product. So therefore this is 1 by s minus 2 into 1 by s minus 1. This is what? L of e power 2t. E power 2t is f of t. So therefore this is L of f of t dot, this is L of g of t. Therefore Laplace of f of t star g of t is L of f of t dot L of g of t, and basically this result will be called as convolution theorem. Okay, anyhow I will write this as separate statement. So let us write this definition at first. Let f of t comma g of t be two functions in the time variable t. Let f of t comma g of t be two functions in the time variable t. In the time variable t. Then the convolution product of f of t comma g of t. Then the convolution product of f of t comma g of t is denoted and defined as f of t star g of t equal to this. I repeat once again, let f of t comma g of t be any two functions in the time variable t. Then the convolution product of f of t comma g of t is denoted and defined as f of t star g of t equal to this integral 0 to t f of capital T into g of small t minus capital T dt. Now you write this example followed by this evaluation. The next one is convolution theorem. Now based on this example experience, we can proceed to convolution theorem. It states like this. The statement of convolution theorem is Laplace of f of t star g of t. Laplace transform of f of t star g of t is Laplace transform of f of t dot Laplace transform of g of t. This is the statement of convolution theorem. That is, the Laplace transform of convolution product of two functions is the product of their individual Laplace transforms. This is very useful in getting the inverse Laplace transform of product of two functions in the variable s. Okay. So again I will discuss during inverse Laplace transform session. So for the time being you can note down this. Laplace of f of t star g of t equal to L of f of t dot L of g of t. L of f of t star g of t equal to L of f of t dot L of g of t. Next concept, initial value theorem. Initial value theorem. Suppose f of t is a function whose Laplace transform exists. So the Laplace transform of this function is f of s, which is nothing but integral 0 to infinity e power minus st into f of t dt. This is the Laplace transform of a function small f of t. Now in this case the function takes its value starting from 0 onwards. Therefore the initial value of such functions is given by initial value equal to f of 0 equal to limit t tends to 0 f of t. So this is the initial value of the function in terms of time variable. But in terms of signal variable, this is limit s tends to infinity s into capital F of s. Here as t tends to infinity, s tends to infinity. Basically time variable is inversely proportional to signal variable, or indirectly we can say that s equal to 1 by t. So because of this reason, as t tends to 0, s tends to infinity. This is my function f of t. Assume that its Laplace transform exists. So by definition, it is a definite integral, integral 0 to infinity e power minus st into f of t dt. It means that the function takes its value starting from 0 onwards. Therefore, the initial value of such function is given by f of 0. So in terms of f of t, this is the limit t tends to 0 f of t. But instead of f of t, if its Laplace is given, then you can express this in terms of limit s tends to infinity s into f of s. If a Laplace transform is given, initial value is given by this rule. If the function itself is given, you can apply this. So both are equivalent. Here t and signal time and signal variables are inversely proportional to each other. Note this point. Let f of t be a function. Let f of t be a function for which the Laplace transform exists. Let f of t be a function for which the Laplace transform exists. Then the initial value of f of t is given by, then the initial value of f of t is given by initial value equal to f of 0. Then the initial value of f of t is given by initial value equal to f of 0, that is equal to limit t tends to 0 f of t. That is equal to limit t tends to 0 f of t. That is equal to limit s tends to infinity s into capital F of s. That is equal to limit s tends to infinity s into capital F of s. The reason is this. Now we proceed to final value theorem. So this is my f of t whose Laplace transform is given by this. Whose Laplace transform is given by this. So therefore the function ends its values at infinity. Therefore its final value is given by f of infinity. So this is limit t tends to infinity. So when t tends to infinity, s tends to 0, because they are reciprocal to, inversely proportional to each other. Note this point. Let f of t be a function. Let f of t be a function for which the Laplace transform exists. Let f of t be a function for which the Laplace transform exists. For which the Laplace transform exists. Then the final value of f of t is given by, then the final value of f of t is given by final value equal to f of infinity. Then the final value of f of t is given by final value equal to f of infinity, that is equal to limit t tends to infinity f of t, that is equal to limit t tends to infinity f of t, that is equal to limit s tends to 0 s into f of s, that is equal to limit s tends to 0 s into f of s. Now the next concept is evaluation of definite integrals using Laplace transforms. Evaluation of definite integrals using Laplace transforms. Let us see how to apply Laplace transforms to get some definite integrals. We can start directly with few problems. Let us start with problem number 1. Suppose we need to evaluate integral 0 to infinity e power minus 2t into t square dt. I want to evaluate this integral 0 to infinity e power minus 2t into t square dt. If I don't have Laplace transform techniques, my alternative choice is evaluate this by using integration by parts applied following by the limits. So it takes some time, but if you apply Laplace transform, this will be very simple. This is integral 0 to infinity e power minus 2t into f of t dt. Here f of t is t square. So here s value is 2. Therefore, this is nothing but Laplace transform of f of t when s is 2. Now, what is the Laplace? What is f of t? F of t is t square. What is s value? 2. So, therefore, this is nothing but Laplace of small f of t when s is 2. Laplace transform of t square is 2 factorial divided by s cube. Replace s by 2. 2 factorial is 2. So, 2 by 8. So, this gives the value as 1 by 4. Note this. Now let us solve one more problem on this. Let us evaluate integral 0 to infinity e power minus t into cos 3 td. E power minus t into cos 3t dt. So here this is f of t and s value is 1. S value is 1. F of t equal to cos 3t. Therefore, this integral is nothing but Laplace of cos 3t when s equal to 1. Laplace of cos 3t equal to s by s square plus 3 square when s equal to 1. So, therefore, this is s by s square plus 9 when s equal to 1. So, replace s by 1, the value becomes 1 by 10. Here s value is 1, f of t is cos 3t. So, this integral is nothing but Laplace of cos 3t when s is 1, which gives me 1 by 10. Now let us solve one more problem on this. Integral 0 to infinity t into e power minus 3 t into sin t dt. Integral 0 to infinity t times e power minus 3t sin t dt. This is somehow complicated integral because we have three functions: exponential, polynomial, sine function. Now this is nothing but integral 0 to infinity e power minus 3 into t sin t dt. So this you can call it as f of t, and s1 is s is 3. Therefore here s value is 3. F of t equal to t sin t dt. T sin t. Therefore this integral becomes Laplace of t sin t when s equal to 3. Now this example we had already discussed in the previous session, that is Laplace of multiplication by t power n. So Laplace of t sin t is 2s by s square plus 1 whole square when s is replaced by 3. So 2 into replace s by 3, 6 by 3 square is 9, 9 plus 1 10, 10 whole square is 100. So therefore this value is 3 by 50. This the thing is you can call it as f of t and apply multiplication by t power n rule. We get 2s by s square plus 1 whole square. Replace s by 3, it gives my 3 by 50. Now we discuss a basic trigonometric formula just like cos of a plus b, cos a minus b, sin a plus b, sin of a minus b to get the Laplace transform of sin square t, powers of trigonometric functions like sin square t, cos square t like this. If I ask you to find Laplace of sin t, sin 80, it is a simple task for me. But if you ask me what is Laplace of sin square 4t or cos cube 3t, cos square 4t like this, powers of trigonometric functions, then we need some basic formula, and then we discuss Laplace of powers of trigonometric functions. The basic formula cos of a plus b is cos a into cos b minus sin a into sin b. So when you have plus symbol, we get minus symbol here. Now cos of a minus b, this gives me cos a into cos b. If it is minus, I get plus sign. Then this gives sin a into sin b. Cos a cos b plus sin a sin b. So this is formula 1, formula 2, formula 3. Let us write the same thing for sin function. Sin of a plus b equal to sin a into cos b plus cos a into sin b. One sin function followed by cos. But in case of cos terms will come at a time followed by sin terms. Now next one is sin of a minus b. In case of sin formula, if it is plus, you get plus. If it is minus, you get minus. Whereas in case of cos, it is reverse. If it is plus, we get minus sign. If it is minus, we get plus sign. So sin of a minus b equal to sin a into cos b minus cos a into sin b. Now I want expression for cos 2a in terms of sin, and I want the expression for cos 2a in terms of sin function as well as cos function. First I will try to get the result in terms of sin, followed by result only in terms of cos. Let us try to this. Let us apply formula number 1. Suppose if b equal to a implies formula number 1, this formula 1 becomes replace b by a. This becomes cos 2a equal to cos a into cos a. This is cos square a minus sin a into sin a. This is sin square a. So in this formula, I am replacing b by a. So that cos 2a becomes cos square a minus sin square a. If I want result only in terms of a, then this cos square a is replaced by 1 minus sin square a. So this is 1 minus sin square a minus sin square a, because cos square a plus sin square a equal to 1. Therefore this cos square a is nothing but 1 minus sin square a. Now therefore this is 1 minus 2 sin square a. Therefore from this we are getting this cos 2a equal to 1 minus 2 sin square a. So 2 sin square a equal to 1 minus cos 2a. So therefore sin square a equal to 1 minus cos 2a divided by 2. This is one of the useful result. That is, we got sine square a in terms of linear function. The advantage is, if you ask me Laplace of sine square a, the power of a is 1, therefore you can easily get this. And even the power of cos is 1. So the main advantage is this, you need not worry about a value. So similarly, if I want this in terms of cos square a, then the expression for cos 2a is cos 2a becomes sine square a. Now I am expecting result for cos 2a in terms of only cos function. Therefore, this is cos square a. This is sine square a is replaced by 1 minus cos square a. Therefore, this is 2 cos square a minus 1. Therefore, 1 plus cos 2a equal to 2 cos square a. Therefore, the expression for cos square a equal to 1 plus cos 2a divided by 2. So we got cos square a in terms of cos 2a like this. Sin square a in terms of cos. Note all these formulae. Laplace of cos square a or Laplace of sin square a. Suppose I want Laplace of cos square 3t. So assume that this is a value. So we have formula for cos square a. This is 1 plus cos 2a divided by 2. Actually what I am expecting is I want Laplace of cos square 3t. So assume that 3t is angle A. Cos square A is 1 plus cos 2a by 2. Therefore replace a by 3t. Cos square 3t equal to 1 plus cos 2 into 3, 6. So this is 1 plus cos 60 divided by 2. Therefore this is Laplace of 1 plus cos 60t divided by 2. 1 by 2 is constant, so you can apply linear property. This is half into Laplace of 1 plus cos 60. Again apply Laplace linear property. This is Laplace of 1 plus Laplace of cos 60. So therefore this is half into Laplace of 1 is 1 by s. Here a value is 6. Laplace of cos 60 equal to s by s square plus a square. This is 1 by 2 into 1 by s plus s by s square plus 36. Note this point. Suppose if you want to calculate Laplace of cos cube t. So earlier to get Laplace of cos square t, we have expanded cos 2a. So similarly to apply Laplace of cos 3t, I will go for cos 3t formula. Now let us see, to get cos 3t, here a and b is to be replaced by a. Now let us see this at first. Here cos 3a, b is replaced by 2a. So cos 3a equal to, this is cos a into cos 2a minus this is sin a into sin 2a. So therefore cos 2a is 2 cos square a minus 1 into cos a minus, because this sin a into this 2 sin 2a is 2 sin a into cos a. Therefore this one is 2 cos cube a minus cos a minus this is 2 into sin sin square a. Sin square a is 1 minus cos square a into 1 cos a. Therefore this expression gives me, this is 2 cos cube a. Here also you will get minus into minus plus 2 cos cube a. So therefore this is 4 cos cube a minus cos a minus 2 cos a. This is minus 3 cos a. Therefore, in this formula, if b is replaced by 2a, then cos 3a becomes 4 cos cube a minus 3 cos a. Therefore, from this, the value of cos cube you can get easily like this. Here cos 3a equal to 4 cos cube a minus 3 cos a. So therefore, in this case, cos cube a equal to cos 3a plus 3 cos a divided by 4. So therefore in this case cos cube of t. Replace a by t. This becomes cos 3t plus 3 cos t divided by 4. Therefore, we got cos cube t in terms of linear functions. Therefore, the Laplace of cos cube t equal to 1 by 4 into Laplace of cos 3t plus 3 cos t. Apply linear property. This is 1 by 4 into this is s by s square plus 9 plus 3 into this one is s by s square plus 1. So therefore this is 1 by 4 into s by s square plus 9 plus 3s divided by s square plus 1. So like this we can get the Laplace of cos cube t. Let us apply this formula. I want cos Laplace of cos cube t. Therefore if I want Laplace of cos square t, I expanded cos 2a. So similarly to get Laplace of cos cube t, expand cos 3a. So take a is a only, but b is replaced by 2a. So we got cos 3a equal to this. So finally cos cube a equal to this expression. Now they become linear functions. Apply a Laplace, we get this. In the similar way, when you try to find sin 3a, the formula becomes like this: 3 sin a minus 4 sin cube a. So note these points. Thank you so much. The session is over.